Extreme value theorem is going to be one of three main theorems that you're going to learn in AP Calculus, along with intermediate value theorem and mean value theorem. I personally think that extreme value theorem is probably the hardest out of the three theorems that you're going to learn. But honestly, it's not that bad. You just have to know a couple things and then you'll be able to solve most problems. So what is extreme value theorem, which I'm going to refer to as EVT from now on for the sake of my sanity. Okay, so let's say that we have a graph, just a regular graph, and that it has closed endpoints. The fact that these endpoints are closed is very important. So remember that it's got closed endpoints. And then our graph just runs between the two endpoints. We'll call this graph F. So this is graph of F. And then these endpoints have an x-chord of, well, this one specifically has an x-chord of b, and this one has an x-chord of a. So EVT states that on the graph of f, I'm going to write this down, bear with my poor handwriting if you can't read it. On the graph of f, on closed is very important that it's closed. On closed interval, a to b, if f is continuous, then f has an absolute maximum, which I hope you know from your pre-calc days, and it's important, that's also important too, and an absolute minimum. So looking back on our graph of f, we can see that our absolute minimum is also going to be this endpoint, which is going to be important later. Know that these endpoints, let me write this down, endpoints can be absolute extrema, and then I'll put it like a star or something. Our endpoints, or specifically this endpoint is the absolute minimum. And this point right here is our absolute maximum. Cool, and that's basically the gist of EVT. So, let me draw a graph where the endpoints are both the absolute extrema, just to drive that point home. So you can see here that this is the absolute maximum. This is the absolute minimum. So yeah, just really drives that point home. Okay, so yeah, that's basically what EVT is. So chances are, if you're going to be doing an EVT problem, you're also going to have to figure out the critical points. So what are critical points? Critical points is just where the derivative of whatever graph you have. Let me write this better. Jesus. The derivative at whatever point, or yeah, your derivative of the graph is going to be 0 or undefined, which I'll just shorten as und. And this is a point important because wherever the derivative of f is equal to 0 or is undefined, that's where absolute extrema are, specifically the x coord. So yeah, that's basically all you need to know about EVT. Just that on the graph of f on closed interval a to b, if f is continuous, that's also really important. That's continuous on the interval. And we're going to have to prove continuity when we eventually do our practice problem. So hopefully you did good in unit 1. If f is continuous, then f has an absolute maximum and an absolute minimum. And critical points is just where the derivative of the graph is, just wherever the derivative of the graph is 0 or undefined, and that wherever the derivative of the graph is equal to 0 or undefined, that's where absolute extrema are, specifically the x coord. Okay, let's roll into our practice problem. I got 3. Okay. Find the absolute extrema on the given interval f of x is equal to x squared over x minus 2 on the closed interval 3 to 5. So the first step of any EVT problem, and we know this is an EVT problem because we're trying to find the absolute extrema. The first step of any EVT problem is proving continuity. So let me write this out better. Let me do that in white. So I'm just writing down our initial function and our interval. So we have to prove continuity first. So hopefully when you look at this graph, you can see, or this equation rather, when you see this equation, you can automatically tell that f is continuous for all real numbers except for x equals 2. So technically, or never mind. I was thinking too far ahead. I was thinking that you have to think this was a critical point because that's because the parent function is going to be undefined, but remember that the critical point is where the derivative is undefined. So not exactly. There's not even a derivative of x equals 2, so just never mind. Okay, where was I? Yeah, that f is continuous for all real numbers except for x equals 2. So that means f is discontinuous at that moment. But luckily for us, we only care about this closed interval. We only care about this closed interval. And since that x equals 2 is outside of this closed interval, that means technically our graph is going to be continuous on this closed interval. So we've proven continuity on this interval. Because, excuse me, because x equals 2 is the only discontinuity. I'll just abbreviate that as discont. It's the only discontinuity, but it's outside of interval. And then since this is a closed interval, that means we can use EVT. If this was an open interval, like it was written with parentheses instead of brackets, we wouldn't be able to use EVT. So since this is a closed interval using brackets, EVT is good to go. Cool. Now, our next step is to find our critical points. Our critical points. So, to find our critical points, we have to take the derivative. We can use quotient rule for this. So, f prime x is equal to, let's see, 2x x minus 2 minus x squared 1 over x minus 2 squared. And then we have to figure out where this is undefined at. So according to this equation, the derivative is undefined at x equals 2. So that's one of our critical points. Because if you plug into this derivative, I guess it works. Okay, whatever. When you plug in 2 into this derivative, you would get 0. And then dividing that by you're cooked. So, okay, I guess I was wrong earlier. I'm just saying things at this point. So yeah, there's one of our critical points. And then to find the rest of our critical points, we have to plug this or set this derivative equal to 0. So let's do that. Kind of running out of space, but whatever. We can just scroll back. Just do some algebra. You have 2x, x minus 2 minus x squared is equal to 0. Going up here, I'm gonna expand this out. So you have 2x squared minus 4x minus x squared is equal to 0. Combine like terms, factor out x, and then we can see that x, our derivative is equal to 0 at x equals 0 and x equals 4. So there's all of our critical points. We have 0, 2, and 4. Now we have to look back on our interval. So since our interval is 3 to 5, that means this isn't included and this isn't included. So the only critical point that we care about is x equals 4. Now our next and close to final step is to make a table of our parent function, not our derivative function, our parent function. And then just find out the y values. So for our x values, we're going to use the endpoints of our domain, because remember that for according to EVT, our endpoints can be the absolute maximums and absolute minimums. So we had to make sure to include that. So we include our endpoints and our critical point. So we have 3, 4, and 5. And then plugging back into our, you can't see that. Okay. Plugging back to our parent function over here, just plug and chug. So when we plug in 3, we get not, excuse me, I'm dehydrated. We get 9 over 1, which is just 9. Let me write that 9 better. I don't, this looks like it. I don't even know what that looks like. Just not 9. Okay. We have 9. Plugging in 4, we get 16 over 2, which is 8. Plugging in 5, we have 25 over 3, which is approximately equal to 8.33, repeating. And then we are basically done. Now we just have to figure out which x value yields the highest y value and the lowest, well, I guess technically f of x value. That's just the whatever our, we have to figure out what x value yields the highest f of x value and the highest or the lowest f of x value. So according to our table, 3 yields the highest f of x value of 9, and 4 yields the lowest f of x value of 8. So that means our absolute max is at 3, 9, and absolute min is at 4, 8. There's our answer. Cool. Okay, next problem. Find the absolute extrema on the given interval. That is the same problem. Hold on. Okay, here's what I'm talking about. Find the absolute extrema on the given interval 2x cubed minus 3x squared minus 12x plus 5 on closed interval -2 to 3. Cool. Okay, so first step, prove continuity. Prove continuity. So since this is a polynomial, hopefully you know that all polynomials are continuous on all real numbers. So f is continuous for all real numbers. And since this is a closed interval, and not an open interval, that means EVT is good to go. So now we do our critical points. Next step is the critical points. Our initial function is 2x cubed minus 3x squared minus 12x plus 5. Taking the derivative, 6x squared minus 6x minus 12. This is also a polynomial, so f of x or f prime of x is not undefined anywhere, so we don't have to worry about that. So all we have to do is set this equal to 0 now. We can factor out 6. This is the same as that. Then we can factor out, or we can just factor this. This is I think yeah. It's equal to 0, so that means our critical points are at x equals 2 and x equals -1. Going back to our interval is -2 to 3. Both points are included. So yeah. So in our table, we're going to do x, f of x. We're going to include our endpoints, -2, and then our critical points, 1, 2, 3. And then you can just plug and chug. I don't feel like doing that much mental math, I'm not gonna lie. I'm gonna just use a calculator. This is what I got for my values. Sorry for the cut. I didn't feel like doing all that mental math, so I just used a calculator. Chances are EVT is going to be calculator inactive. So I wouldn't recommend using a calculator like I did, but for just for teaching purposes for me. Yeah. So now that we have our values, we just evaluate which x value gives the lowest, y value, which x value gives the highest. So we can see that our absolute max is at -1, 12, and our absolute min is at -15, 2, -15. There's your answer. Okay, I'm scrolling back to this repeats, and I forgot. Oh, and by magic, I fixed it. Wow. Okay. So first step. Okay. Find the absolute extrema on the given interval. F of x is equal to x cubed minus 12x on closed interval 0 to 4. So first step, prove continuity. Hopefully this is getting these steps are getting through your heads right now. First step, prove continuity. This is a polynomial again. This is a polynomial again, so that means f is continuous for all real values. And since this is a closed interval, we're good to go for EVT. This is going to be the last practice problem. Good to go for EVT. Next step, critical points. Our parent function is x cubed minus 12x. So our derivative using power rule, 3x squared minus 12. This isn't undefined anywhere, so we're not gonna have to worry about critical points at undefined values. So we're just gonna set this equal to 0 now. Do some algebra. So here's what I got for my critical points. Looking back on our interval is 0 to 4. So that means -2 is not included, so we don't have to worry about that. So this is the critical point that we only care about. The only critical point we care about. Make a table. Include our endpoints and our critical points, and then plug and chug. So we have plugging 0 into our parent function. Let me not draw a line through this stuff. Plugging in our stuff, when we plug in 0, we get 0. 2, we get 8 minus 24, which is -16. And 4, we get 64 minus 48, which is 16. Looking at our table, which values give us the lowest value and the highest value. 2 gives us our lowest, 4 gives us our highest. So our absolute max is at 416. Our absolute min is at numbers. Okay, do -16. Let me write this 6 better. And yep, there we go. So as you can see, it's just a very formulaic process. Once you get enough practice, it just becomes automatic at a certain point. So yeah, that's EVT.